Thank you for joining us for this ECIS webinar dealing with the theory of ECIS. My name is Charlie Keese, and I'll be your host for this approximately 30-minute long webinar. Sometimes the slides may update slightly behind the audio, so please just be patient. The basic idea of ECIS, or monitoring cells using impedance measurements, came about a number of years ago when Ivor Gaver and I were at the General Electric Research and Development Center. There we realized it was possible to grow cells upon gold electrodes and, applying weak AC signals, monitor some of their behaviors. This idea has caught on and is now commercially available. And of course, the heart of all of these systems will be the special wells where the electrodes are located, where the cells will be grown. In this case, we're looking at one of our electrode arrays, which has 8 wells. And at the bottom of each well, there is a small 250 micrometer diameter electrode. Of course, this is an electrical measurement, so we have to complete the circuit. And to do that, we have a counter electrode, which in this case is very large and is labeled CE in the middle panel. But the impedance will go inversely with the area, and so the counter electrode has a very low impedance, and almost all of the measurement will be of the small electrode, which can hold from a single cell up to maybe 50 to 100 cells in a confluent layer. With this small electrode, if we look at the actual measurement, we're going to use tissue culture medium as our electrolyte, and we're going to apply a very weak AC signal. We want it to be weak because we want to essentially monitor the cells non-invasively, so they're unaware of the measurement, so we don't affect them in any manner. The other thing to always keep in mind when you make an impedance measurement of cells is that there is a parameter which would be the frequency of the AC signal, which always has to be specified. In a lot of our early work, this was at 4,000 hertz, as is suggested at the top of this slide. We're going to apply a constant current. This is dictated by the electronics, and we'll monitor the voltage across the electrodes. Now we can simply take that ratio of the voltage and the current and apply Ohm's law. It's that simple to get the impedance of an AC circuit, which is measured in ohms, the same as with a direct current measurement. This is what we would refer to as monitoring the simple impedance. But quite a bit can be done with this before we deal with complex impedance, which makes the measurement quite a bit more richer. But let's first consider simple impedance. If we apply this current at 4,000 hertz and inoculate one of these small electrodes with 2 different types of cells, seen here, African green monkey kidney cells, BSC1 cells, or normal rat kidney cells. As the cells attach and spread, we see the impedance going through a striking increase from about 2,000 ohms of the open electrode up to maybe as high as 15,000 ohms. These cells attach and spread at different dynamics. Accounts for the difference in the curves, but they happen to go to about the same final impedance. This could be quite different if you were looking at cells that had tight junctions, which would be off the top of your monitor, or very weakly attached fibroblastic cells, which might have a smaller effect on the total impedance. Once the cells have achieved their confluence, we see there are fluctuations in the curve, which we term micromotion. This is biological in nature because notice the bottom trace is what we see if we simply have a well without cells present, just a flat line. These micromotion measurements can be of interest. They also can be somewhat difficult when one's looking for overall changes in the change in an impedance, because these are kind of random motions, random impedance signals due to the motions of the cells. They are of use, though, in many measurements, but sometimes we like to get rid of them, and we do that by using much larger electrodes. For example, here you see an 8-well array which has 40 electrodes in each well. And there are other different patterns that we use where we have interdigitated fingers. So in these cases, we'll monitor the impedance over many more cells, and that will tend to decrease the presence of the micromotion. For example, look at this curve. Here we've inoculated the same cell type on both a 1E array, where it has that single 250 micrometer diameter electrode, and one of the arrays that has 40 of these. Now, these will have very different overall impedance values, and so we have normalized the impedance in this case by dividing it by its starting value. And the starting value is with confluent layers of cells. The confluent layers receive fresh medium about an hour into this run, and we see the response of the impedance due to the change in morphology of the cell. Notice with both the single electrode or the 40 electrodes, the overall trend is the same, but by using additional electrodes, we quiet the micromotion and have a smoother trace to see the overall effect of the fresh medium upon the cell layer. The micromotion, though, is very important when studying toxicology, and that's a topic of another webinar, and so it is something we use these 1E electrodes for. But in general, most work now is done with additional electrode area to calm the micromotion and see overall trends in the impedance changes. So the difference here is looking at maybe 100 cells as opposed to 4,000 cells on the 40 electrode array. We can even quiet these micromotions more with what we call a cell proliferation array. Here we're looking at one of these which has large interdigitated fingers. The cells are inoculated at the yellow arrow at different concentrations, and we follow them for over a couple of days, looking at the increase in cell numbers due to cell division, with almost no micromotion showing. Now, why do we see these changes? Here's an oversimplification, where we see the cells, cartoon versions of course, coming down on an electrode that's carrying current. The current, of course, is being carried by ions in the solution from the electrolytes in the tissue culture medium. Here we're suggesting that the cells come down and actually blanket the electrode. That actually removes part of the electrode from the measurement and would cause an increase in impedance, much the same as if you were to put any insulating film, in this case small plastic bags filled with saline, on the electrode. If you block the electrode surface, the impedance will increase. But this is an oversimplification because, as is well known, cells don't blanket their substrates, but rather they are up off the substrate standing on adhesion plaques. Here's a very attractive micrograph of adult human fibroblasts where we've stained for the adhesion plaques and some of the microfilaments and so on. And what you see is that the cells are actually attached by small focal adhesions, and the bulk of the cell is not directly on the substrate. So if we return to our cartoon version of the cell, this is a better way to look at it. The cells are on adhesion plaques. We don't show them actually touching here because we want to show the current paths, but the current has two ways it can pass through the cell layer. One, shown by the solid red arrows, is to simply flow in the solution paths underneath the cells between the electrode and the basal membrane, and then through the pericellular space between the cells. But notice there's a dotted line also here. And that's to indicate, because this is an AC, not a DC measurement, we can couple through the insulating cell membranes by charging and discharging the membranes as the current oscillates back and forth. And this capacitance that we monitor through the insulating cell membranes depends upon the AC frequency. And that is very important, so I'll circle it here, when one is studying the behavior of cells electrically using impedance from an AC measurement, because it will depend on the frequency. Let me show you a dramatic example of this, just using this idea of simple impedance, and point out the difference of using different AC frequencies. Here's a cartoon version of the cells again, where we think about how the current paths will look at high AC frequencies. And when you're doing ECIS measurements, high frequencies will usually be above 40,000 hertz. Again, current will follow the path of least resistance. The red arrows indicate current flowing through the solution under the cell and through the paracellular space, whereas the large green arrows are indicating that current can couple capacitively through the membranes. At high frequency, this path through the membranes, it becomes very low in impedance, but low in reactance, and most of the current will choose that path. On the other hand, if we turn the frequency down to say less than 2,000 hertz, now current cannot couple easily through the membranes capacitively. The green arrows are much smaller here, and instead the current chooses the path under and between the cells. Let's look at this with some actual data. Here, we've inoculated 2 electrodes with MDCK cells that form tight junctions. We're adding enough cells at time 0 to go to confluence. And we're following these same electrodes by switching the frequency back and forth from 40,000 hertz to only 400 hertz. And we see very different patterns in the impedance. Notice on the left-hand side, at high frequency, at that first dotted line, about 3 hours after inoculation, these cells have essentially plateaued. But if you look on the right-hand side, the same wells, the same cell layers, at 400 hertz, at that first blue line, the impedance has barely come off its starting value, and it's not until later, maybe 10 hours after inoculation, that we clearly see the impedance at 400 hertz plateauing. If you look at these cells at these 2 different times indicated by the blue lines, 3 hours and 10 hours post-inoculation, this is what you see. At 3 hours, the cells are in place. They have attached, they have spread, but if we stain them for the tight junction proteins Z01 or E-cadherin, notice they're very diffuse at 3 hours. But at 10 hours post-inoculation, clearly the tight junctions have formed. These stains are now localized at the junctions between the cells, and also we see the F-actin, the microfilaments, taking a very different pattern. What this is saying is that by simply changing the frequency from 40,000 hertz to 400 hertz, we can look at 2 different aspects of cell behavior. High frequency is looking at cell substrate coverage, whereas lower frequencies are probing the paracellular space between the cells. Again, we have to make a lot of assumptions here because we're only using simple impedance. But we can refine our understanding of this quite a bit if we instead monitor what we call complex impedance. Let me go and back to this slide that we've already seen where we looked at Ohm's Law, where we're simply monitoring the voltage after we apply a known current to get the impedance in ohms. But if you remember, in addition to resistance in AC circuits, there is reactance. And reactance, also measured in ohm, comes about by having either capacitance or inductance in the circuit. Now, inductance comes from having coils. But outside of the electronics we're using, when you look at the actual electrodes, cells, and tissue culture medium, there is no inductance. But there is capacitance. And so this is the circuit we're actually representing when we look at the cell layer at different frequencies. We have a pure resistance and we have a capacitance, and we're treating these as though they're in series. Remember, current can flow through a capacitor even though there's an insulating space between the two metal plates by charging and discharging each plate. The higher the frequency, the more readily the current can couple through the capacitor, or we would say the reactance is lower. So now when we take the measurements using ECIS, this is what the current flow looks like and the voltage. The current we're applying is the dotted red line. It has a certain frequency. The voltage we measure, the solid black line, will have the same frequency. But the important point here is the two are not directly in phase. Notice the current and voltage peak at different times. One would say that the voltage is lagging the peak in the current by a certain number of degrees, treating one full cycle of the current as a complete 360 degrees. And so that phase angle, that phase change indicated by the Greek letter phi here, is what the more sophisticated instruments will be monitoring to get complex impedance. And once you have that amplitude and that phase angle, now instead of just reporting the impedance, one can report the resistance and the capacitance that's being measured. So now a better way of representing our cells on the electrode is using the idea of tier, which is the resistance under and between the cells, which is commonly measured on filters in ohm centimeters squared. And we also have the membrane capacitance. And although the instrumentation is treating the circuit as though is a series AC circuit, it can be easily converted into this parallel arrangement. Again, if we think about the curves we looked at before monitoring simple impedance at low and high frequencies, here's what we would see with this circuit, this parallel RC circuit. At low frequencies, the reactance of the capacitor is extremely high, and so the current will instead take the path of least resistance through the solution, the tier. Whereas at high AC frequencies in the lower panel, now the tier is still there, but passage through the capacitor, through the cell membranes, becomes so low in reactance that almost all of the current will choose that path. So how do cells affect the resistive portion of the impedance at different frequencies? Let's just think about the resistance here. Again, this is a complicated graph in a way because it's a log-log plot. We're plotting the log of the frequency on the x-axis from 10 hertz up to 10 to the fifth, 100,000 hertz. And the resistance is also going from less than 1,000 ohms to almost 10,000 ohms. Without cells, this is what this will look like. It's a very complicated curve in a way. The electrode interface accounts for this slope. In other words, the problem of current moving at the interface of the electrode becomes much more easy, less resistance as the frequency goes up. And it keeps dropping, except in the long run, we have the resistance of the solution between the measuring electrodes, and this doesn't depend on frequency. So this log-log plot of what looks like the interface electrode resistance, which is pretty much a straight line, does bottom out and turns over to reach this constant solution resistance. That's a complicated graph. Main thing is, how does this change when the cells go down and attach and spread and form a confluent layer? And this is what we see when cells are present. what we find here is that there is kind of a sweet spot where the difference between the electrode with cells and without cells shows the most change. And that is approximately where I've drawn this red arrow. Again, this is the frequency where the ratio of the cell covered to the cell-free resistance is the greatest. And while you're monitoring resistive portion of impedance, this is where most measurements are taking place. Usually around 4,000 hertz for endothelial cells, at lower frequencies for very tight cells, and at higher frequencies for very loosely connected cells. That's shown here. We have three different cell types. The African green monkey kidney cell, which doesn't really form a tight junction, MDCK type 2, which have tight junctions, and the NIH 3T3 fibroblast. If we monitor these at different AC frequencies and plot out the resistance with cells to that of the open electrode, each cell will have a characteristic signature. Notice the MDCK cells with their tight junctions are better monitored at low frequencies. The BSC cells, somewhat intermediate between the MDCK cells and the very loosely connected NIH 3T3 fibroblasts. Let's think then about the measured capacitance at different AC frequencies. And I'm not going to show a log-log graph of this, but rather we're going to look again at some actual data. Again, capacitance is best measured at high frequency because at high frequency, the capacitance have a very low reactance. Most of the current will flow through this, and we can essentially eliminate the resistive portion of the impedance. Here's a look at cell attachment and spreading while we're following the capacitance at high frequency. The interesting thing here, it's very different than looking at resistance in that the capacitance, as the cells go down and put their membranes in series with the electrode, will drop. Here, the electrodes have been coated with either fibronectin, laminin, which is the second curve, vitronectin, or bovine serum albumin. The frequency, again, is high, 40,000 hertz. As the cells attach and spread, the capacitance drops. Why does it drop? Well, the electrode itself has a very high capacitance compared with the cell membrane capacitance. But when the cells go down and attach and spread and form a confluent layer, at high frequency, the current is still going to couple capacitively through the cell membrane. But when you put capacitors in series, as is shown here, it drops the capacitance. The capacitance, in fact, can be no higher than the smallest capacitor in a series arrangement. And so that accounts for this change in the capacitance. But if you look at this in more detail, as Professor Wegener shows at the University of Regensburg, if you monitor high-frequency capacitance and watch cells attach and spread and see that drop in capacitance, and at the same time measure using microscopy the area of the electrode that's covered with the cells, it turns out that the capacitance we measure is linearly related to the electrode surface coverage by the cells. This means that if we look at this diagram again, where we had cells attaching on different proteins, we could replace the capacitance because of this linear nature with a percent cell coverage axis as I've shown here. A very powerful tool because you can monitor now the dynamics of cell attachment and spreading and the without using microscopy and area determinations by simply monitoring capacitance at high frequency. Here's an example of this where we're looking at MDCK cells again attaching and spreading. They're inoculated at time 0. The electrodes here, I believe, have been coated with gelatin or fibronectin. I'm not certain. But notice there are 2 green traces and 2 black traces. In the case of the black trace, the salt concentration of the medium has been modified such that the only divalent metal ion present is magnesium. The green traces are where the only divalent metal present is calcium. There are subtle differences in these curves, but essentially, looking at this drop in capacitance, we know that the cells are attaching and spreading approximately at the same rate and forming a complete cell layer. But now, if looking at these same 4 electrodes at low frequency and monitoring the resistive portion of the impedance, notice how strikingly different they are, where only in the presence of calcium are we able to form the barrier function, whereas with only magnesium present, these cells are showing essentially very little change in resistance. That's the power of having complex impedance and using different frequencies. And we can take this to the extreme where we monitor cells at a variety of AC frequencies and then apply a mathematical model that's built into our software. By clicking with a click of a mouse, you can turn data, and instead of reporting capacitance or resistance, you can report 3 different parameters that are shown here. Now, to model data, one always has to be careful because you have to make some simplifying assumptions. And the 2 that are apparent here first is that if you look on the right-hand side of this, the cells are treated as though they're disks. Also, we don't show any adhesion plaques. We treat the cells as though they're hovering over the surface by a distance h. And there are 3 parameters that the model will give back. One are time course changes in RB, which is the problem of current going through the paracellular space between the cells. It also returns values of the membrane capacitance, the combined capacitance of the 2 membranes, and the term alpha, which relates to the spacing of the cell, the plasma membrane over the gold electrode. And you can see the actual formula that is used in H, where H is evaluated with the radius of the cell and the resistivity of the solution to give alpha. Now, this is complicated because it's mathematical modeling. But again, what we're doing here is by taking data at different AC frequencies, we're reporting the problem of current going between the cells, the membrane capacitance of the cells, and the problem of current moving in that cleft between the electrode and the basal membrane to get to the paracellular space. Here's some actual data comparing 3 different cell types, looking at different values that the model returns for RB. RB is measured much like TIR in ohm centimeters squared. And you can see HUVEC cells, which endothelial cells are of great interest in knowing more about their barrier function, are approximately almost 30 times lower in terms of barrier function than the MDCK cells with its tight junctions. And we also see values of alpha here. The higher the value of alpha, the closer the cell is to the substrate, or the larger the radius of the cell. Here's some raw data looking at 4,000 hertz, monitoring some, I believe these are HUVEC cells that are being treated with a fairly high concentration of thrombin. The red trace is the control. The cells are confluent, the thrombin is added. We see a drop in the resistance and a return in a few hours back to nearly control levels. Let's take these same data. Again, you would have them measured at different frequencies, and you'd simply call up the modeling software. And instead of time course changes in resistance, we look at time course changes in RB and alpha. Membrane capacitance tends not to generally change in most experiments, but RB and alpha can. And here we see thrombin addition clearly is dropping RB to 0 values, and then it returns. In other words, the barrier function of the cell is completely compromised, and they are fully permeabilized by that level of thrombin. Because the model now is only designed to work with confluent layers of cells, it automatically drops out and does not at that point report alpha until the value of RB comes back. But it's clear using the model that we can point out that thrombin, and this is no surprise, is causing a change in the paracellular space between the adjacent endothelial cells. Well, that's what I wanted to cover today. These measurements are all made using our ECIS Z-theta instrumentation. This can connect either to a device in the incubator that holds 2 of the 8-well arrays or a 96-well arrays. And they come with different patterns of electrodes, as we discussed earlier. Our website is biophysics.com. You're welcome to visit there and learn more about this method. There are lists of publications and so on. Also, we're hopeful we may be attending a trade show in March, but I doubt it. And also, our ECIS school, which we hold here regularly throughout the year, has been put on hold due to the pandemic, but we hope that will return as things get back to normal. I appreciate you coming out for this webinar. We have them every other week in general. 2 weeks from today, there will be one talking more about the invasion of endothelial cells by metastatic cells and how we can monitor that. And then 4 weeks from today, on February 2nd, we'll talk about monitoring cell migration using ECIS. If you'd like more information, want to schedule a demo of an instrument and so on, please contact us. Here you can see the name of some key people, Catherine Toniati and Michael Detweiler. If you're interested in demoing, want to know more about pricing and so on, they would be good people to contact. Also, if you would like copies of these slides, I'm happy to give them to you. Just email me. I'm at keese@biophysics.com, and I'll send them to you electronically, and you can use them as you see fit. So again, thank you for joining us for this webinar. We certainly look forward to hearing from you in the future, and I hope you found this somewhat useful. So stay healthy. And Happy New Year, everybody. Hope to see you again soon. Bye-bye.